Hello, this is summary of lecture 27 in positive definite matrices, and here I will discuss about the last topic that is in the book and also in the lecture, which is about the ellipsoid in Rn, which having this equation that we see earlier, the polynomial equation that is derived from the matrix, and we set it to be equal to 1. And that will be result into some kind of this ellipsoid thing in the graph. So for an example, I will take a one in the book. So we have this matrix, and this is also about how we use the factorization that we learned earlier from the symmetrics lecture here. So I will just quickly put it here. So these are all the two eigenvector, the 1 1 and 1 minus 1, and these are the eigenvalues corresponding to each of them. So the eigenvalues of 9 has the eigenvector of 1 1, and then the eigenvalue of 1 has the eigenvector of 1 minus 1. Okay, and then if you can see that this is exactly the Q, this is lambda, and this Q transpose. Okay, and then in the book it's also mentioned that you can convert this further into this form, this X transpose as X, and if you multiply in both sides by some vector, then you will have Q transpose X. See, so this is where we start with, and this is where we end up with when we multiply the X on both sides. Okay, and then this will be equal to, if you just follow along, let me just compute a little bit because it is not done in a book. So this will give us, let's see, and then you can have this, you pull that out, x plus y, x minus y, and 0 0 1, x plus y, x minus y, half 9, x plus y, x minus y, half x plus y, x minus y, and then you will have 9 x plus y square over 2. Actually it will be let's just do it one by one here. We pull those out, the square of 2, square of 2, and then we have here the 9 to this x plus y square, x minus y squared, and this is where we have the plus sign here, right? And if we plug them in, we have a 9 x plus y squared over 2 plus x minus y squared over 2, or if you want to, in the book it is written as x plus y square root square, a root of 2 square plus x minus y square root 2 square. Okay, and from here what I understand from the point of the book, that the coefficient that has that is tucked in here, the 9 and the 1 here, let me just write it that 1. So those things are coming from the eigenvalues here, 9 and 1, and that will determine like how far the eigenvectors are stretched. Okay, and let me put it here first. So there are two ways to look at things, right? So if I were to say this as big X and this as Y, then I have an equation of 9x squared plus capital Y squared equal 1. Oh, don't forget that I equal all of this to be 1. Okay, so I have 1 here. And you see that this is the ellipsoid equation with a radius of 1. We put a boundary of 1 into this equation, so what we have here is some sort of like this. Okay, while here I also drew this earlier. I just want to bring this to the attention of this is coming from this equation. So if you have this equation of 5x squared, remember, so if we compute the x transpose as x, so this is what we will have in the equation, plus 8xy plus 5y squared, and this is what we will have, and we will have this axis here, so this will be pointing to the direction of 1 squared minus, okay, so this will be with the eigenvalues of 1, and while this one will be the thing with the eigenvalues of 9. Okay, while this picture coming from this, so this is pointing to here and here. Okay, and this is with the eigenvalues of 9, and this is with eigenvalues of 1. Okay, so first I just want to like redo this exercise that is done in a book and how to get into this point, because it's in the book it's not really mentioned this extensively, how do you get to this point. And then another thing is that you see this coefficient again, this 9 and 1, this is coming from the eigenvalues, which is tell you how stretched that axis is, like the how big those eigenvector goes, those axes go. Okay, and second of all, you can see that from these two pictures they're kind of similar, they're coming from different equation, but they're still preserving the same idea of having these two axes here and here, and they are stretched by the value in the eigenvalue, right? And it turned out that the bigger eigenvalue gives shorter axis, and that's why here you see the one with the eigenvalue of 9, it has a shorter arrow, while the other one has bigger arrow with smaller eigenvalue, and the same thing happened here. And if you check the book, that's also the idea of 1 over the eigenvalue, right? The square root of eigenvalue, apparently square root of eigenvalue. So that's the point. And also lastly is that this thing called here, that's why this thing is called the principal axis theorem. If you remember from previously, this factorization has two names, either the spectral theorem or the principal axis theorem. And this is called the principal axis because, again, you see that it kind of gives you the idea of that axis, that main axis that construct this ellipsoid in the R, and in this case the two-dimensional R. Okay, so again, to recap, this equation right here, this factorization, is principal axis theorem because it explains to you the axis and how far it stretched, and how far it stretched is determined by the eigenvalues here, in this case the 9 and 1, and then the bigger lambda eigenvalue gives the shorter axis, as you can see here. And maybe I will create another video to explain more and give more example about this. But that's the idea of this topic right here, this part 3. And that's it. Thank you.